Alright, gang, here we go. This is Physics, Unit 3, Part 4. We're going to talk about momentum and impulse in this video. Okay, now, so let's just recap for a second what all we've talked about over the course of the year. So we talked about kinematic equations, right? And this was, several weeks ago now. So kinematics, the kinematic equations allowed us to predict the motion of, we did projectiles, we did motions in one direction. Okay, it allowed us to predict motions. Okay, so that was the kinematics job. And then we talked about Newton's laws. Okay, right, in Unit 2 we talked about Newton's laws. And Newton's laws allowed us to predict how force affects the change of the motion, right? And then in this chapter here specifically, we're talking about momentum and impulse. Okay, momentum and impulse allow us to figure out exactly exactly how the duration of the force on a collision or some sort of action affects the motion. Okay, so specifically, Newton's law talked about forces and how that changes the motion, and then now we'll talk about how if we make that force occur in a short amount of time, then that'll change certain things, or if we spread out that time, that'll also change certain things. So in order to do this, we need to introduce a new concept here, and it's called momentum. Okay, momentum is a word you've probably used or heard a lot in your, just in everyday life. Okay, and this is how we calculate it. It's defined as mass times velocity. Now, momentum, notice how it's with a bold in this thing. That means it's a vector. Okay, so mass is a scalar, velocity is a vector. So momentum is always a p, a lowercase p. I'm not really quite sure why it's a lowercase p, but that's what we use to represent momentum, and it's defined as the mass times the velocity. Okay, so essentially the momentum is just a relationship between how massive the thing is that's moving and how fast it's going. Okay, and and so it's directly proportional to both of those. So if you take a ball and you throw it faster, it's going to have more momentum. If you take that ball and you just throw it really slowly or roll it on the ground, it's going to have less momentum. The SI units for it are these guys here, kilograms times meters per second. And that makes sense, right? Because mass is in kilograms, right? And velocity is in meters per second. Okay, so that's momentum. Now, if we think about this for a second, we've talked about this guy. This is Newton's second law, F equals ma. Okay. Now, if we think about what you've now learned about momentum, and we take this formula here, and we solve it out, we see that, well, delta P is equal to mass times the change in velocity, right? And if we take that over delta T, well, we know that velocity, so let's pull that mass out here. So the velocity is the change in distance over the change in time. So that'd be distance over time, and then divided by time again. So that would become mass times the distance over time squared, right? Or this is essentially acceleration, meters per second squared. So really, these two things are exactly the same, right? Those are equivalent. And in fact, we taught you this was Newton's second law when we taught it to you, but that's not how Newton originally wrote it. He originally wrote it as this guy here, the change in momentum over the change in time. Okay, so that's how he originally represented it. So it is true still that the force is equal to the mass times the acceleration. However, it's also true that if we have rapid changes in the momentum or changes over time, that is a representation of force, right? So think about it this way. You've all caught, imagine you're playing catch with, a friend with a baseball, right? And neither of you have gloves. Okay, and they throw the ball nice and easy underhanded to you. It comes to you, you catch it, right? And it didn't take much energy to catch it, right? You took it, it's no big deal. Okay, now you throw it back, and then they think they're going to be funny. They're going to launch it at you, and they friggin' chuck it. They throw that sucker really hard. It comes at you, and you catch it in your hand, right? You manage to catch it, but how does your hand feel afterwards? Well, if you've done this before, you know your hand is starting to sting. It's stinging because your hand had to exert more force in order to stop that ball, right? That makes sense. So because the ball had a bigger momentum, then that means it took more force to stop it. Okay. Also think about this way as well. Like think you're taking you're on a trampoline. Okay, so you're standing on a trampoline, all right, and you jump up in the air. Okay, you get a good foot off the ground or something like that, and you fall back down and you land back on the trampoline. Right? How much did that hurt? Well, it doesn't hurt at all, right? Because the trampoline. Well, let's increase the value here. You jump and you go and you land on your rear end, right? You land on your rear end and you sink down and it bounces you back up, right? And the spring absorbs that. So if you think about the amount of change, the time portion of your change, right, was extended out, right? Because the trampoline went down and kept that. So that change in momentum occurred over a long period of time. Now imagine you go out to your sidewalk and do the same thing. You jump a foot and a half in the air, and you come and you land on your rear end on the sidewalk. Well, that cement ain't gonna move for you, right? So the change in time is going to be really, really small. So it's going to exert a large amount of force on your rear end, and you're going to have a broken coccyx or something like that, right? So that's kind of what we're talking about here, all right? So because of that, we get this idea. It's called the impulse and momentum theorem, all right? When we take our force and multiply it by our change in time, that gives us the impulse. Okay, so remember the momentum is equal to mass times velocity. Okay, and impulse is known as the change in momentum. Okay, and remember the change in momentum. All right, so let's just write this out here. Change in momentum is going to be P final minus P initial. Okay, and we know that momentum is equal to mass times velocity. Well, mass is going to be the same, so it doesn't have to be final. It's just going to be the same, times the velocity final, and then minus the mass times the velocity initial. Okay, and so this would be our change in momentum here, mass times the velocity final minus mass times our velocity initial, and that gives us this idea down here. So this formula is very, very important. Okay. So if we take our force times whatever time interval we get, that gives us our change in momentum. All right, so these are the units for it. The SI unit is Newton meters, or kilograms times meters per second, and these should look very familiar to you. These are both joules. Okay, so impulse is essentially a change in momentum. So remember, acceleration was a change in velocity. Same relationship here. Okay, impulse is the change in momentum. It's essentially just another version of Newton's second law. Okay, so the change in the momentum depend on two things. It depends on the force being applied and the amount of time over which that force is applied. All right. So think about it this way. Okay, if you've got a car or a truck here and it's coming up to a stoplight, okay, and you put the brakes down all the way to the ground, right? You didn't realize there was a stop sign coming. You slam on that brake and you come to a stop, right? If you're driving an empty car, okay, you have less mass, so it doesn't take as long to stop. Okay, if you're driving a loaded car, with the same force, it's going to take a longer time, right? Because your momentum has to change, because your momentum, remember, is equal to the mass times the velocity. If your velocities are equal, but the mass is greater here, it's going to need a longer amount of time to stop. So therefore, because it takes a longer time to stop, it takes a longer space to stop as well. Okay. So that's kind of the idea of impulse, and momentum. It does take some practice trying to think about all these things. So, okay, I've got more mass, so therefore it's going to take longer to time, and then think about, like, all of the nice thing is all of this stuff is very intuitive. Okay, the problem I found that students have is that it's using these new physics words to represent it. Like, if you can represent it in everyday language, then this is quite easy to grasp. However, when we start putting in a physics vocabulary, that's where students start to get confused. So really, really, really practice using the physics vocabulary when you're doing these practice problems in your head. Okay, don't let yourself get trapped into this, well, if I just think about it in the way I'm used to, because then when you're on the quiz or the exam or something like that, and you're like, wait, what? Like, I can't quite remember what this was, etc. Life gets more, that's when you start running into problems. Okay, so let's do a practice problem here using momentum. Okay, so it says a 1,350 kilogram car has a velocity of 22.0 meters per second. When braking rapidly, it stops in 4.5 seconds. What is the momentum of the car before braking? Well, we know that momentum is equal to the mass times the velocity. Well, the mass is 1,350 and the velocity is 22. So the momentum would have to be equal to 1,350 times 22. We get 29,700, and we need 3 sig figs, so it'd be 2.97 times 10 to the fourth. All right, 2.97 times 10 to the fourth, and the units for momentum are kilograms times meters per second. Okay. And that's what I got earlier too. Oh, I forgot this. So it should be divided by kilograms times meters divided by seconds to the north. All right. So that's our momentum. What is the magnitude of the force required to stop the car? Well, we know force times delta t is equal to the change in momentum. Okay. Well, when we go from our initial momentum is going to be this value here. Our final momentum is going to be 0 because we want to stop, right? Change in momentum, remember, is equal to final minus initial. Okay, so this guy here is going to be 0, right? Because it's going to have 0 velocity, and this guy here is going to be the 2.97 times 10 to the fourth. All right, and it says its magnitude. Remember, we see the word magnitude, and we automatically think of absolute value. Okay, so anyway, absolute what am I thinking? Value. Okay, so anyway, absolute value. So our force is simply going to be equal to the delta P over delta T. Our delta P is going to be this guy up here, 2.97 times 10 to the fourth, because we're starting there and we're ending at 0, and we're dividing it by our time, which is 4.50 seconds. So we take 2.97 times 10 to the fourth divided by 4.5, and we get 6,600, and we need 3 sig figs, so it would be 6.60 times 10 to the third, and this would be in newtons, right? Because this is a force value, so it would be newtons. All right, and that matches what I got earlier today, which is good. All right. Another idea that I want you to be able to calculate is stopping time. So how much time it takes for something to stop given its velocity and the mass that it has. Okay. Notice that no matter if you're stopping quickly or slowly, your change in momentum is always going to be the same, because momentum is only determined by mass and velocity. Your mass isn't going to change, right? If it does, we can still take care of that. But our velocity is going to change. If we're stopping, our final velocity is always going to be equal to 0, which is nice. So when we're stopping, so just keep that in mind. We'll maybe make a note of that. When we're stopping, our final velocity is equal to 0, right? So increasing the del time decreases the force that's involved. Okay. So we already talked about this trampoline idea. You could also think about airbags, right? So imagine you're in a car wreck, right? And so you're in a car wreck, car hits you from behind, and it hits you hard enough for your airbags to go off, and so the airbag, so you're getting flung forward because you got hit from behind. The airbags go off, and then instead of making you stop suddenly when your head slams into your steering wheel, okay, you slow down. You slow down over time because the airbag is slowing down your thing. So your impulse is slower. So therefore your force is lower. Okay, so decreasing that time interval or getting rid of the airbag and you slam into it increases the force. So just imagine the difference, if you were trying to hit a hammer or hit a nail with a hammer, if that nail had a pillow on top of it, it would be a lot harder to hammer that nail in, right? Because a bunch of your force would get lost into changing, this impulse being increased. Okay, so anyway, so that's kind of the idea here. So let's do a practice problem here. So a 65 kilogram passenger in a car travels at 8 meters per second. If the passenger is stopped by an airbag in 0.75 seconds, how much force is required? All right. So force is going to be equal to the change in momentum over the change in time. Well, the change in momentum is going to be just whatever the initial momentum is. Okay. So it would be the mass times the velocity. So 65 kilograms times our speed, 8.0, and we're going to divide that by our time, 0.75 seconds. All right, so we get 65 times 8 divided by 0.75, and we get 693.333333. All of these guys have 2 sig figs, so it'd be 6.9 times 10 squared newtons. All right, so that's how much force would be exerted on the passenger. So that's still quite a bit of force, even with an airbag, right? So, but what if the airbag, I mean, it doesn't have an airbag? So you're driving an older car, or maybe a car that had an airbag that deployed that never got replaced, okay? And you're stopped in 0.026 seconds when you strike the dashboard, okay? So your time, instead of it being 3/4 of a second, is 3/100ths of a second, essentially. All right, so your force is going to be equal to, same idea here, change in momentum over change in time, okay? And your change in momentum is going to be the exact same as it was before, right? Because it's the same mass and the same speed. So it was 65, okay, 65 kilogram passenger traveling at 8.0 meters per second, and your change in time now would be the 0.026 seconds. All right, so we take 65 times 8 divided by 0.026, we get 20,000 newtons, okay, or 2.0 times 10 to the 4th newtons, okay? So that's how much it's going to stop, but it doesn't ask for that. It says at what factor does the force increase. So in order to get the factor that increased, we're going to take that, we're going to divide it by the force that we found before, which was 6.9 times 10 squared newtons, right? So we'll take the 20,000 divided by the 690. And I got 28.985, so that's about 29. Let's just say that 29 increase. 29 times increase. I didn't really phrase that right, but whatever. So it'd be increased by 29 times. It's 29 times greater force. Okay. So that's it for this part. Do your practice problems. This stuff can be pretty confusing, so take your time doing those practice problems. Ask questions when you got them, and I'll see you on the flip side.